Great. Welcome, everybody. I'm so glad that you could all join us for our first virtual event. My name is Kenji Hakuta, taking over tonight for Aviva O'Neill, who is the Great Basin National Park Foundation Program Manager, who is joining us. You'll see her little icon on the screen, but is having some internet connectivity problems. So I've been asked to host. I am the Professor of Education Emeritus at Stanford University in the Graduate School of Education, and I have the pleasure of serving on the board of the Great Basin National Park Foundation, and also chair the Education and Outreach Committee. In tonight's program, we'll be hearing from Dr. John Kenny, also a Great Basin National Park Foundation board member, and also the operations chair of the GBO. As well as two GBO scientists that he will introduce. The presentation will be about 30 minutes long, followed by Q&A. If you're new to Zoom or have never used the question and answer feature, let me give you a quick short introduction. If you take your mouse and hover it over the bottom of the screen, a toolbar appears and you'll find the Q&A feature there. So down here, you'll see the Q&A feature there. And please enter your questions anytime during the presentation, and we'll monitor that and answer them after the presentation. Before jumping into the program, we know that many of you are joining us tonight are new to the Great Basin National Park Foundation and the GBO, and many of you may even be new to the park itself, the Great Basin National Park. So we wanted to start this program tonight with a short video introduction to you, for you to introduce you to the park and to the foundation and some of our programs.
Hi, I'm Aviva O'Neill, Program Manager for Great Basin National Park Foundation. In case you haven't been to the park, I'd like to start by giving you a short introduction. The park is located in a remote section of eastern Nevada, next to the Utah border. The park, established in 1986, preserves an outstanding segment of the Great Basin. It is a place to sample the stunning diversity of the larger Great Basin region, from the 13,000-foot summit of Wheeler Peak to the sage-covered foothills below. The park has a myriad of distinctive geological features, such as Lehman Caves, rock glaciers, alpine lakes and meadows, and boasts 13,000 years of human history. It is a place to marvel at the majesty of nature and connect to a deeper sense of time. High in altitude on the steep rocky cliffs live bristlecone pine trees, the oldest living individual organism in the world. Some of these trees are over 5,000 years old. And looking up above at night, there exists a window into the universe. With the darkest and most stable skies in the contiguous United States, Great Basin National Park interprets and protects an amazing and threatened resource, a truly dark sky. Visitors come from all over to gaze and wonder at the cosmos. Park rangers host astronomy programs on a regular basis throughout the summer, and each year in the fall, the park puts on a spectacular 3-day astronomy festival. Great Basin National Park Foundation is the official nonprofit partner of Great Basin National Park. We were founded to help foster people's connection to the park so that it is preserved, enhanced, and protected for future generations. In tandem with the Park Service, we develop forward-thinking advocacy, education, and visitor experience initiatives for the park and the entire Great Basin region. In 2015, we constructed the Great Basin Observatory, a project dreamed up by a Great Basin park ranger. The GBO is the first research-grade observatory ever built in a United States national park. Set at an elevation of almost 7,000 feet, with no significant man-made light for 70 miles in all directions, the observatory is a state-of-the-art, remotely operated, optical, astronomical telescope, which allows researchers to explore astronomy and science from the park's pristine dark skies. 4 university partners work with us in the Great Basin Observatory project. The Great Basin National Park Foundation also partners with the park to deliver youth education. The building of the Great Basin Observatory inspired us to create science education curricular resources for teachers, which are made available on the Great Basin Observatory web portal. We work in Great Basin area schools, connecting children to the park through classroom presentations, field trips, and material resources and trainings for teachers. Our goal is to encourage students to engage in science and conservation more deeply through place-based learning and to treasure the Great Basin region in which they live. The Foundation supports these programs and projects as well as many others. I hope you'll choose to learn more. Go to our websites, greatbasinfoundation.org or the Great Basin Observatory.org. And I hope that you'll choose to become a member, become a guardian of Great Basin and help support all of these great programs and projects, as well as the Great Basin area and Great Basin National Park.
Thank you. Thank you for your patience. Now I'd like to turn this over to Dr. John Kenny, who will introduce the rest of the program.
Good evening and welcome. I'm Dr. John Kenny, Professor of Chemistry and Chemical Physics at Concordia University and Director of the Chemical Physics Laboratory Summer Research Institute at Concordia. I also serve as Chair of the Operations Committee of the Great Basin Observatory and member of Great Basin National Park Board of Directors. Tonight is my distinct pleasure to introduce Cole Niebuhr, President of Global Science Directive. Cole's research style is characterized by amazing breadth and originality, as we'll see tonight. Cole also serves as Science Laboratory Manager and Adjunct Professor of Chemistry at Concordia University. He has taken a leadership role in the development of the spectroscopic and Speckle Interferometric research capabilities of the GBO and in training students how to use the GBO for astronomical research. Joining Cole tonight is Ruth Larson, a senior physics mathematics double major and honors student at Concordia who has spearheaded spectroscopic software development initiatives at the GBO. She is an active GBO researcher. Cole and Ruth, take it away.
Well, thank you very much, Dr. Kenny, for that introduction. It is an absolute pleasure for us to be here today and share with you some of the research that we've been up to over at the Great Basin Observatory. One of the, a fun fact about Dr. Kenny before we get started is that he has successfully run a summer research institute for the last nearly 20 years over at Concordia University. Because of the problems with COVID this year, it was looking like we might not be able to continue that tradition. However, because of the just incredible resource that is the Great Basin Observatory and the remote access that it allows us, we were able to continue that research this summer. And I'm very excited to share with you the work we've been up to these last couple of years and particularly over this last summer. Pardon me just a second. Get rid of that stupid thing. All right. Sorry about that. So again, my name is Cole Niebuhr, and I'm the president of Global Science Directive, which is a nonprofit 501c3 scientific research company located in Southern Nevada and Southern California. It is, in addition to our research, we work with other nonprofit institutions, including Concordia, which has provided me the amazing opportunity to also serve as a professor there and work with a lot of the outstanding students that we have. One of the key students being Ruth Larson, who's joining me today. And as you can see here, I just got married 5 weeks ago to a wonderful young lady, and we were able to get married over at Concordia at the chapel that they have there. So Concordia has been just such a huge blessing to us, and it's a true pleasure to be able to work on advancing the science program. Before I jump into everything, I want to introduce a little bit about the telescope. The Great Basin Observatory is a 0.7 meter telescope located at the Great Basin National Park. The combination of a really high elevation and that desert climate gives us just a really crystal clear seeing. The light, there's no water in the atmosphere to really scatter the light, and lets us see things very clearly. It's the remote location keeps the skies especially dark, and it's just an incredible resource to work with. Because of its remote location, we had to come up with some inventive ways to be able to work with it. And what makes it such a powerful tool and unique tool is that it's completely robotic. People can access this telescope from all over the world and do some high quality research. A lot of the basic systems of the Great Basin Observatory is automated. So you can use a web app to access it and tell it, this is the stars I want to look at, or the planets I want to try to look at. Here's the coordinates, here's the camera settings, and it'll go ahead and take all of those requests and put them together and then figure out the most efficient way to go through all those requests and save the data for you. For some of the more advanced techniques, which aren't currently automated, we do also have the ability to remotely access all of the computers at the observatory and work with them exactly the same way that you would from your own home computer. Albeit with like a little bit of a lag time between the signals, but it works out pretty well. There's 4 computers at the Great Basin. The first one is the weather computer, which I have on my left monitor there. And the weather computer just monitors the weather and environmental conditions around the observatory. It has the ability to override the rest of the observatory. So if it determines that conditions are unsafe, it's able to shut down the whole systems and cause the whole system to go into sleep mode, allowing it to weather a storm or avoid some snowfall or whatever it may be. There's a lot of other attributes that, on that computer as well that just help us in controlling the overall telescope, but we don't need to go into all those details right now. On the center console there, I have the GBO control computer showing, and the control computer does exactly that. It allows us to control the dome, open and close it at will. Allows us to point the telescope wherever we want it, and move the mirrors, move the focus, allow us to direct the light that's coming into the telescope to whatever pieces of instrumentation we want to work with, and so on and so forth. We have control over every facet of the observatory that I can think of, from all the individual power outlets even. It just gives us a great amount of control in the telescope so that we can do whatever we need to accomplish. The other 2 computers are the spectroscopy computers and the Speckle computers, which are some of the more advanced techniques that we've recently been able to bring online over at the GBO. Those aren't yet automated, but we're working towards that. We'll go into more detail about spectroscopy and Speckle, but just kind of in a nutshell, spectroscopy allows us to study the way that light interacts with matter, and allows us to determine a lot of important the important characteristics of some of the objects that we're looking at. And then the GBO Speckle is essentially our equivalent of a microscope, and it allows us to zoom in on a system that we're looking at and resolve some of the finer details of that system. So diving in, our research has been working with the double stars. Double stars come in 3 different categories. We have our optical doubles, which means that from our perspective on Earth, there's 2 stars that appear to be close to each other. But in actuality, in 3-dimensional space, they may be separated by an enormous distance, and are therefore not particularly we're not particularly interested in that for our research. The more interesting ones are the visual binaries and the non-visual binaries. A binary system is whenever you have 2 stars close enough to each other to gravitationally interact, and they orbit about each other. And the reason why we're interested in this is we can't directly make measurements from a lot of stellar phenomena, be it planets or stars or black holes. We have to infer some of those characteristics by looking at their behaviors, in particular how they interact with other systems. We work with double stars because that allows us to measure the gravity that's going on between the 2 stars. But you can also do that to measure the gravity between a planet and a star, or a black hole and a star. We've been working with double stars simply because they're large objects and they're easy to see. A visual binary is something that we can clearly see as two separate stars using standard observations, and a non-visual binary is going to be something that requires a little bit more of our advanced techniques, being like the Speckle system, for example. So we can't clearly see that there's two separate stars there until we use those techniques and can resolve the individual pieces. But the overarching goal of this project is to be able to measure some of the important characteristics of stellar phenomena, in particular mass. The mass of a star is probably the most important a piece of information that you can have about the star, as many of the other characteristics are largely dependent on the mass of the star. And so in order for us to find the mass of a star, in order for us to get its weight, we have to look at how much gravity it produces, because gravity and mass are directly correlated. And in order for us to do that, we need to find two stars that are close enough to each other so we can clearly see how gravity causes their movements to shift. So this process is kind of a stepwise process. It starts off with basic photometry, and then it moves into calculating orbits, then gathering spectral information, and then doing a lot of math to end up figuring out the data. What's really excellent about this process is each step in this process is a bit more complicated than the preceding ones, and this gives us a great pipeline for educating students. There's no point in working at a university and doing research if we're not also including students in the equation and allowing and fulfilling our roles as educators. Photometry is a pretty standard basic system. It's just us taking a picture of the stars, making a couple measurements. But it's the most basic level of research that we can do. But what it does do is allows us to introduce students to the telescope system, how you can control the telescope, how you can start collecting some of this data, how you write scientific papers, and a lot of just really great foundational techniques. As we progress through this system, we can get into the orbits and spectral information, which is good for our sophomore and our juniors, and even some of our seniors. But for some of our seniors, like Ruth Larson, who specializes in math and physics, it also allows us to get her introduce her to some of the great astrophysics. Really just as a result of all this, she can get into many amazing grad school programs, and it just really sets her up as just a top tier candidate. What's really great about this system is that it's progressive and that it's using this remote telescope. So this is not just a program that we can use at Concordia, but something that could be easily implemented at any other university that's so inclined. So the first step in this is the standard photometry, and that's going to be exactly what that word means. Photo, like taking a picture, and metry, meaning a measurement. So we can take a picture of these two stars that we're looking at, and we can measure then the angle between the two stars, and with respect to north, and also the distance between the two stars in arc seconds. And what we do with that information, which we have there in that first table, is we take several, like 10 of these images, find an average and a standard deviation, and that's our new data point. Stars can take several decades to even several centuries in order to make a full rotation. So we have to take our data point with historically recorded data points, which is managed by the US Naval Observatory. We can take all those data points and put them together to ultimately, as shown in that top right image, start seeing the curvature of the orbit, and that allows us to start calculating what the orbit start doing the math to calculate an orbit that would explain the gravitational interactions. We can also take this information and combine it with other important pieces of information. For example, data taken from the Gaia project. The Gaia project was a satellite system that was launched by the European Space Agency, and it looked at billions of stars over its lifetime and determined their distances from Earth. This is important because if we're looking at these two stars, we want to make sure that they're a true binary and not just an optical double. So if we know their distances, if both of the stars are roughly the same distance from Earth, and they're both moving through space at they're both moving northeast at the same speed, then we are pretty sure that they are gravitationally bound. Especially if you start, if you can combine your data over several years to start seeing that curvature of the orbit, so you're able to know it for sure. But as you can tell from this image right here, stars, they're not just white points that we can very clearly see. You can see that there's like a little bit of a halo around this particular image, and that's just caused by the light that scatters as it enters our atmosphere. A great example is the sun. The sun is essentially a perfect sphere, or pretty close to a perfect sphere, but it doesn't look like a sphere when we see it from Earth. We can see that sphere, but it's surrounded by this halo and this glow and this aura that's around it, and that's just caused by the light that's coming from it scattering as it enters our atmosphere. As a result, if we have a couple stars that are fairly close to each other, that aura, that glow, can obscure our ability to see one of the stars. And there's or environmental contamination, or there's noise that comes from our instruments, and there's all these things that can contribute to making it really difficult to see a secondary star. So in order for us to resolve that, we use something called Speckle Interferometry. Speckle Interferometry is one of those advanced techniques that we just successfully got working 3 weeks ago. This is something we've been working with on and off for a couple years, and we were able to finally get it working a couple weeks ago, much to our excitement. That picture there on the left is a picture of a double star. That, if you can kind of make it out there in the middle, it just looks like a blur of light. It looks like a little blob. And that's because these stars are a little faint and they're really close to each other, so it's really difficult to resolve them. And there's a lot of noise that can obscure some of that light, like by the light scattered through the atmosphere, or some of the built-in noise into the instrumentation. Anytime an electrical current goes through our system, there's going to be a couple of these pixels that light up. So what Speckle Interferometry allows us to do is take hundreds of these images and stack them on top of each other, and start identifying which of these pixels are lit up by noise, are coming from noise, and which of these pixels are being lit up from the stars themselves. What's important to remember on that image on the left is that is a picture of a double star. So that means all the information is there. We just need to be able to find a way to access it. And that's the essential purpose of Speckle Interferometry. Instead of taking a 1 second or 2 second or 3 second picture, we might take a couple hundred 20 millisecond pictures. And we want to do these really short burst pictures because we want to see that noise that's built into the machine very clearly. Once we stack all those images on top of each other, if we can clearly see what's noise and what's not, it's really easy for the system to resolve what of these pixels are being lit up by an actual star system. And as a result, we end up getting the picture that's there on the right, where we can clearly distinguish the two stars. What's really powerful about the Speckle system is that at a distance of about 5 arc seconds, it's difficult for us to resolve one star from the next star. But with the Speckle system, we can get that down to about 0.2 arc seconds. This allows us to look at double star systems that only a handful of observatories are actually able to look at. If you look at the Washington Double Star Catalog, which has all this information about double stars, there may be several dozen historical observations for many of these star systems, but for the ones that are really close to each other, under that about 5 arc second limit, there might be only 3 or 4. So one of the great things about the Great Basin Observatory is we're able to interrogate systems that are largely ignored or unable to be studied simply because of the technical challenges associated with it. So that's kind of the basics of photometry, and a little bit more of the advanced photometry. But what's important now is what do we do with that information? And to do the heavy lifting here and explaining some of the hard stuff, I want to introduce you to Ruth Larson. Ruth Larson is a student at Concordia University, and she's been working with Dr. Kenny and I for about the last 3 years. We've done some of our best work on her, and we love showing her off. So with that said, I'm going to turn things over to her.
Thank you, Professor Niebuhr, for that introduction. As mentioned earlier, one of the most important things that we can know about a star is going to be its mass. Unfortunately, you can't go out and weigh a star, so you have to find the mass of the star in a different method. And we can actually do that using Newton's laws of gravitation as well as Kepler's laws of planetary motion, which states that if two objects are caught in each other's orbit, in this case, double stars, then they will trace out an elliptical path. And if we can plot that ellipse and see what path they're taking, we can determine the dynamical mass of the double star system, which means we can't determine the individual masses of the stars, but we can determine the masses multiplied together, which will be very useful for us. In order to do this, we have to use photometry as well as Speckle to take a whole bunch of pictures of these stars and see how their separation and their angle with respect to north differs. However, because the orbital period of these stars can be 10 years or 50 years or 100 years or anywhere in between, it takes a long time to gather data. So what we do is we grab a whole bunch of data from the Washington Double Star Catalog, as Professor Niebuhr had mentioned, and we take that data as well as our new data, and we try to plot out an ellipse from this. Sounds pretty simple, right? Not quite. Unfortunately, the ellipse that we're looking at is not always going to be the actual ellipse that the two stars are orbiting in. Why? Well, if you look at the picture to the bottom left, imagine the black screen is our field of view. That's what we can see. The flashlight on the top would be very ideal. It's pointed straight at us, directly 90 degrees to our plane of view. And therefore, whatever the flashlight projects onto our field of view, that's what we see. It projects sort of a circle or an ellipse there, and that's exactly what we see. However, most double star systems are at an angle to our field of view, and so they don't look like the top flashlight. They end up looking like the bottom flashlight. This flashlight is the same exact flashlight. It's projecting the same exact shape. However, because it's at an angle, what we see is going to be a parallel projection of the true ellipse onto our field of view. So not only do we have kind of a whole bunch of images with a whole bunch of random dots that we're trying to draw an ellipse on, but it's also not the true ellipse of what the stars are actually doing. So in order to correct for this shift in angle according to our field of view, we have 7 orbital parameters which will define both the true orbit, which we're trying to solve for, as well as the projected orbit that we see. And those would include the period of the double star system, which is in time, and it's just how many years or fractions of years that it takes for the secondary, the smaller star, to orbit around the primary star or the bigger star. We also have T, which is the time at which the two stars are closest together in their orbit, which would be called the periastron. We have the semi-major axis of the ellipse, A, which is just one of the measurements of kind of how squished the ellipse is. And then the eccentricity, which is also another measurement of how round or oblong the ellipse is as well. And then 3 of the parameters will describe how the ellipse system is oriented in space. And those are just 3 angles which determine how we can solve from the true orbit, or from the projected orbit to the true orbit. Once we have this true orbit, that's when we can solve for the dynamical mass of the system. However, that really doesn't give us much. We really need the individual masses of the 2 stars in order to determine where they are in their life cycle, or what elements they're producing, etc. In order to do this, we have to use a technique called spectroscopy, which is, as previously mentioned, is the interaction of light with matter. This is a very very wonderful technique that we just implemented at the Great Basin Observatory recently. As you can see, Professor Niebuhr's campsite out there in the frigid cold for a couple of weeks. He had to go up there and tighten a few screws and put in the spectrograph and whatnot. So we're very excited about this technology at the Great Basin Observatory. In order to understand how spectroscopy helps us solve for the individual masses of the double stars, we have to understand a little bit about physics, unfortunately, or fortunately. I'll leave that up for you to decide. Basically, when a light wave, because it's a wave, when it interacts with an atom or a molecule and it hits an electron, if you look at the top right, the electron, if it's in the bottom left of those target type things, if the light wave hits the electron can jump in an energy level and it raises the energy state. And then the electron has absorbed the photon of light, so the light is no longer there. The electron can release the light later if it wants, or stay in the higher energy level, depending on where it's most stable. What this is really useful for is when you look at a star, it's going to be putting off all the wavelengths of light, all the colors, the entire beautiful rainbow of light. However, if there's an element in front of the star that the star has made through nuclear fusion, it's going to absorb some of those individual wavelengths of light and remove them from the beautiful rainbow. So what this does is only certain wavelengths of light are going to be absorbed by certain elements. It's one specific wavelength of light per electron in a certain energy state. It's very specific. It's practically a fingerprint for an element. So just by looking at the spectrum of these wavelengths of light, you can determine which elements the star is actively fusing and what elements are around the star that it's currently made. However, it's not quite that simple. We have to first separate the light because stars give off white light. You just look at our sun, you're like, I don't see any rainbows coming from the sun. So you have to separate the white light into all its component wavelengths and thousands of colors. If you see the picture in the bottom right, we're shining a flashlight of white light through a very, very thin slit. And the light's going to be bending around those slits. And each individual wavelength of light, each individual color of light will reflect off or diffract at a certain angle. So you put in white light and you get out a beautiful rainbow, just like a prism that you would put in your windowsill and you see the rainbow on your opposite wall. The same exact thing is happening here. Spectroscopy, we have an E-shell spectrograph at the Great Basin Observatory. It uses both a diffraction grating and a prism to diffract this light twice and separate it into very high orders that we can look at and analyze. Here's a beautiful example of a spectrum from our sun, actually. Our sun puts out all these colors of light. But what are those dark lines, you ask? Well, they are the elements that are around the sun, that the sun has produced, that are taking away certain wavelengths of light. They have absorbed these wavelengths, and so they're no longer going to be seen in the spectrum once we've separated all the beautiful colors of light from white light into this wonderful spectrum. What's really cool about this is if you notice the darker lines mean that there are more of that element. The darker the line is, the more abundant that element is that our sun has produced, or any star for that matter. But I promised you that this would help us solve for the individual masses of the stars, and I have not held good on that. So how do we do that with spectroscopy? These wavelengths of light, the little black lines, are in specific spots for specific elements. So when you're looking at a star, they're going to be rotating quite quickly. One side of the star is going to be rotating towards you, and one side of the star is going to be rotating away from you. The side that is rotating towards you is going to be putting off the same exact light as the side that's coming away from you. But if you've ever heard a police siren coming at you, and then it sounds higher pitched than when it's going away from you, that's because the sound waves are getting squished. So they sound higher even though they're putting off the same exact sound. And then when it's going away from you, they sound lower pitched even though it's putting off the same exact sound. Same thing happens with light because it acts as a wave. The wave of light that is coming towards you from the side of the star that is spinning towards you is going to look squished, and the wave of light that is coming from the other side of the star, the side going away from you, is going to look expanded, pulled apart. These black lines, because they're in specific points, if the wavelength is longer, the line will be shifted a little bit towards the red side of the spectrum, and if the wavelength is shorter, the line is going to be shifted a little bit towards the blue side of the spectrum. That discrepancy it's called redshift and blueshift. That discrepancy between where the line should be and where we actually see the line, we can use that difference to determine the radial velocity of these stars, which is how fast it's spinning around. Using the radial velocity combined with the dynamical mass of the star system, we can determine the individual masses of the stars, because radial velocity, it will be faster the less mass that you are going to have. And so we can use that to determine the masses of the stars. This is extremely significant to our research because not only can we understand what the stars are made of, what elements they're producing, where they are in their lifespan, we can understand how massive they are. We can know their intensity and how far they are from Earth. And to summarize, we have to use Speckle and photometry to take the data that we're going to use to solve for an orbit, which will allow us to solve for the dynamical mass, or the combined mass of the two stars. And then we can use spectroscopy, which will allow us to solve for how fast the stars are spinning, which combined with the dynamical mass will allow us to determine the individual masses of the stars. And we can solve for the spectral types of stars. And then, once we have all that, we can place them on the Hertzsprung-Russell diagram, which is the picture to your right. The main sequence of these stars is that big branch in the middle. That's where most stars are at, including our sun. And they're burning up, well, not really burning. They're fusing hydrogen into helium and etc. However, there's more than one branch, clearly. Giant branches, they're extremely large stars. They've burnt up all their fuel, and they can get so big. They're not very hot, but they're very large. And then they can suddenly collapse back in on themselves. And then there's the white dwarf branch on the bottom left. And this helps us understand where the stars are in their life, as well as if they might turn into a neutron star, or even collapse and become so small that light cannot escape, and they have become a black hole. And I will turn it back to Professor Niebuhr.
Right, did that work? Okay. All right. So thank you, Ruth. I told you all that we did some of our best work on her, and we love showing her off. And now you know why. The Great Basin Observatory allows us to do just some incredible research. It allows us to study stars, to learn about their life cycle, and to not just learn about that star, but by looking at all the stars in its neighborhood, it allows us to start learning more about that galaxy that it's in. And then by looking at all the other galaxies that are in that neighborhood, it helps us learn more about the universe. All of the amazing things that we've learned about space, the things that inspire us and blow us away, have all been done by astronomy. We have relatively very few missions that have ever really left Earth to do to bring back like data about other stars, to bring data back about other planets, other than a little bit from Mars and the Moon. This is how all this astronomy starts. It's by making these types of observations, and then starting to solve for starting to do the physics to solve for the different properties of stars and neutron stars and black holes and other planets. And it's just a really, really powerful tool, the GBO. It's a great educational tool, and it's something that we are honored to be able to work with on a regular basis. The utility of this telescope is incredible. It's not what we've discussed today is just what we've been doing at Concordia University, but there's so many other applications that are currently being used, such as astrophotography, which is those beautiful pictures of nebula and galaxies, exoplanet research, where we're discovering new planets orbiting around different stars, asteroid studies, looking at asteroids inside of our solar system, not to mention just being able to continue the research in quarantine. But there's even more applications that we aren't currently doing, but we're talking about doing. I myself am not an astronomer. I'm a microbiologist, and I'm very interested in being able to use this telescope in a astrobiology study, which is going to be looking at the physics that life would have to overcome in order to exist on other worlds. A way that we do that is looking at the spectral type of a star and figuring out how much radiation it produces, and then looking at the planets that are nearby it and seeing how far those planets are away, how much radiation that they would be absorbing, and just these kind of physical parameters that life would have to overcome to do there. This telescope provides us with so many incredible research and educational opportunities that go far beyond just astronomy, but is truly interdisciplinary. The spectroscopy itself is largely chemistry, and it's a very, very powerful tool. And in talking about all this, because I just want to thank all of you supporters and all of you guardians of the Great Basin Observatory for just this incredible opportunity that we have working here. We're planning another GBO trip here in the near future. One of the things that we're going to be installing is a meteor camera. Which this camera is a part of a network of hundreds of these cameras all over the planet. And what it does is, as a meteor passes through our atmosphere, it takes pictures, and we're able to solve for the trajectory of that meteorite, figure out roughly where it impacts on Earth, and then a team can be sent out to go collect that meteor, and we can do some space geology. So it's not just the incredible things that we already have at the GBO, but all the incredible things that are going to continue to come. I want to thank all the people who've helped us along the way. This is not just this summer in particular, we've had a whole lot of different researchers that have been able to join us as part of our research institute and have given a lot of clarification to the students. Each of them has provided several guest lectures, and have just been an incredible importance in making this summer's research institute just really productive and powerful. Dr. John Kenny, of course, is our PI, our principal investigator. Paul Garner handles all the GBO operations and makes sure that the GBO keeps running. Then Dave Rowe wrote the programs to do the Speckle system. Rick Hobbs has taught us about research and background using all those different catalogs and the Gaia database. Rick Harshaw has helped us out with the orbital parameters, which Ruth made sound like it's fairly straightforward and simple, but it's incredibly complicated to be able to do. To make a three-dimensional model based off of two-dimensional information. So it's mathematically intensive, and we really appreciated the help of Mr. Harshaw. Rush Dene started us down this road of double stars a couple years ago, which we forgive him for. And then, of course, Aviva O'Neill and Kenji Hakuda for hosting us tonight, and all the work that they do with the Great Basin National Park Foundation. Then, of course, I want to thank Concordia University Irvine for all their support of the GBO, the Board of Directors, the Global Science Directive, and then again, of course, the Great Basin National Park Foundation for everything they do, continuing this program and all of the educational outreach that it's done at the Great Basin National Park. Because it's worth saying again, thank you all so much, all you donors, supporters, and guardians of the Great Basin National Park and Observatory for all that you've done for helping us keep this GBO operational, and for just productive, all this great research we've been able to do, and great education we've been able to do, not just at Concordia, but at 3 other major universities and many more high schools, private schools, elementary schools. We've been able to do work with all sorts of great institutions, and it's just a true honor and pleasure to be a part of this program. For any of you wanting some more information, we're going to transition over to Q&A here, but we also have some contact information with Dr. John Kenny from Concordia, myself from GSD, and Aviva O'Neill from the Great Basin National Park Foundation. We would love to hear from you. We'd love to answer your questions. And with that, we'd like to turn things over to a Q&A section. Thank you very much for having us.
Thank you, and this is such a great example of the value of undergraduate research opportunities, and thank you for sharing, the cutting edge knowledge that you're generating, the learning that you're doing, the passion, the excitement of science conducted in this kind of context. So thank you so much for this great presentation. Aviva, I think you've been monitoring some of the Q&A, but I'd like to just kind of start by asking a question, which is asking if you could share some of the technical challenges that you've found in this work.
Let me start on this one. I think if we had any idea how hard it would be to do this, how much work it would take, and how many hours of frustration are the foundation of what you've seen tonight, I don't know whether we would have done it, but that's science at its essence. It's complexity, its beauty, the amazing highs when everything works, and the disappointments when it doesn't, and the learning that takes place even when everything is falling apart and not happening. It's been an incredible journey. And the really exciting thing is that we've just begun the journey. We're just starting to use the telescope as a research instrument, and it's delivering magnificently.
Thank you, John. So I wanted to read something that someone sent in that Robert Denny sent in with the question and answer. And Robert Denny said, I am the author of the ACP expert software used for GBO data acquisition apart from Photometry and Speckle. Thank you so much. We from DC3 Dreams were there for the opening ceremony and met Becky Mills and others, and it was enchanting. So thank you for that comment. We appreciate that very much, and we're glad that you could attend today. I also have another question here. It's actually from the park superintendent, James Woolsey, and he is asking, what future technologies can we look forward to at the Great Basin Observatory, and what will it help us to discover?
I will happily take that one. The first one that we mentioned, of course, was that meteor camera that we're going to be implementing here in the near future. We already have the meteor camera. We just have to go and install it. And that allows us to start collecting specimens from any meteor impacts in North America, which would be very, very exciting. One of the spectra we showed you earlier from that beautiful solar spectra, that one unfortunately is not a spectra that we are able to take quite yet at the Great Basin Observatory. We don't have a spectrograph of that quite that high of a resolution, but we are currently working on a grant to try to secure the funds to get a much higher resolution spectrograph that would allow us to get some of those very, very fine details. The details we can resolve right now is we can get those fingerprints to tell us what elements are there, but we don't see all the fingerprints. Each of those black lines that was on that before was a very specific electron transition for all these different elements on the periodic table. We can see a lot of those transitions, but not all of them. So that's something that we're very excited about being able to work towards here in the near future.
I have a question for Ruth, which is how this research experience has impacted your educational experience at Concordia. And maybe if you could also share a little bit about how it might have affected your thoughts about what you'd be doing after graduation.
Thank you for that question. Honestly, this opportunity to work with the Great Basin Observatory has been one of the most, it has taught me the most at Concordia. I remember staying up until like 4 a.m. trying to collect information for the spectrograph and trying to work through code that was in French that neither Professor Nebo or I understood. And it taught me so much more about how the scientific world actually works and what you're expecting to put in 12 months of work and then not even have any data sets to show. It's been very enlightening, and it really has been an excellent experience. I definitely want to pursue some kind of mathematics or physics degree, and honestly, in graduate school, and working with the telescopes at the Great Basin Observatory has probably made that my decision for me.
Thank you. You're such an inspiration to us educators. There's a question about where we can find results or of publications from the research that's been done at GBO.
Kenji, I'll actually answer that, which is that we do put everything onto our Great Basin Observatory web portal. So when things get published, which there are quite a few publications, I think there's about 6 right now, we'll link them to the research and action part of the Great Basin Observatory web portal. And please come, we hope all you attendees will please come to the website and look through what we have there. And we're always adding new stuff as more research is taking place.
Here's another question for Ruth. Donald asks, I have a question for Ruth. How did you first get introduced to this research as an undergraduate? And what advice would you give other undergraduates who want to pursue research in physics?
That was in the summer of 2018, I believe. I was working at the undergraduate summer research program with Dr. Kenny, and Professor Niebuhr comes up into the lab. I didn't know him at this time, and he says something like, oh, 7 p.m. I'm going to be at the telescope trying to figure stuff out. This would be Concordia's telescope. And he said, if anyone wants to come join, I'll be there. And so I showed up because it was 7 o'clock and I didn't have anything else to do. And then we started trying to figure out how to get this E-shell spectrograph working at Concordia so that we could implement the same E-shell spectrograph, well, the same type of E-shell spectrograph at the Great Basin Observatory. And we worked and worked and worked on that for about a year, and we finally got it working. And then we started taking observations and working with the Speckle camera, and it has been an absolute wonderful experience. What advice would I give to other undergraduates? Take as many opportunities as you possibly can. If I had wanted to be lazy and sleep in and go to bed early, 7 o'clock, none of this would ever have happened. Grab as many opportunities as you possibly can.
Thank you.
As a follow-up, Ruth's humility is showing right now, and she has done just so much work on getting the GBO operational to the point that she mentioned earlier we were working on some French code to try to get the spectrograph working. Since neither of us know French, we eventually just gave up and designed our own program from scratch. And she was involved in that process from the very beginning. And we ended up writing our own software and pulling it off. That was a huge undertaking for us because, again, I'm a microbiologist, not a computer programmer, and she's an undergrad student, and we ended up teaching ourselves programming and figured out how to do it. So she's been a huge help the entire process.
I do not see any more questions. Aviva, do you want to, if there are other questions, please type it in soon. But Aviva, would you like to wrap us up since you seem to have good audio now?
Sure. Well, and it's perfect. We're just before 7 o'clock. I just want to thank everyone for coming today. Like I said, or like Kenji said in the beginning, this is our first virtual program. And we had a little bit of technology problems there, but thanks for sticking with us. I think this has been a really neat opportunity to see the amazing work that people have been doing with the Great Basin Observatory. And of course, Great Basin National Park, as you can see from the virtual slide behind me and from the video, is an amazing place. Us at the foundation, we're very excited and passionate group of members and supporters who care for the park's resources, and support these type of programs like the Great Basin Observatory and other projects that we do. So we do hope you'll come and check out the website, greatbasinfoundation.org. Get to know us a little bit more if you're new to us. And thank you very much for coming tonight.